All right, good morning, everyone, and welcome to day 3 of the UBC ARC Back to School Bootcamp. This morning, we'll be talking about introducing GPUs on UBC ARC Sockeye. My name's Jeff. I'll be your main instructor today, although in the present room, we have Jerry, our life science specialist, and Jacob, one of our system administrators. We also have Liz in the back corner, the manager of our team, and Eliza, one of our analysts, who will be able to help you out. We'll also be monitoring the Zoom for any questions and comments there. I can't move my slides. All right. So let's kick things off with the land acknowledgement. We would like to acknowledge that the University of British Columbia Point Grey campus is located on the traditional, ancestral, and unceded territory of the Musqueam people. The University of British Columbia Okanagan campus lies on the unceded territory of the Syilx or Okanagan peoples. Thanks, Jerry. So a few housekeeping slides to get things going. For those attending online, you've been muted automatically when you entered the room. This is in webinar format, so you will need to raise your hand if you'd like to be unmuted to ask a question during the presentation. And the webinar is being recorded. The recording for this session will be made available on the ARC website, specifically on the ARC YouTube channel, but linked through the ARC website. Not this week, maybe in a week or so after the course. You should also be able to find the links on the OSF materials site, which we'll talk about in just a moment. So similar to the other courses and those upcoming, all materials for the bootcamp are available in the Open Science Framework at the following link. For those in the room, we've written it up on the board, and materials for today's session are available in the below link. All of the links here in the uploaded deck should also work for you. So there are numerous highlights throughout the slide deck. One thing to know is this is a hybrid learning environment. Also bear with us because this is the first time we've done this post-COVID hybrid-wise, so we're still ironing out some kinks. If you have virtual questions, we have the chat feature disabled by default, so please feel free to ask questions in Zoom. I'll do my best to keep track of them, but we also have our volunteers in the room and online keeping track of the Q&A. Live questions in the presenter room, whether it be here or the Okanagan campus, can be asked by just raising your physical hand, and we will make sure that we address your question for both the Zoom and the in-person audience. And yeah, I think I covered that in the last one. One last thing, almost last thing, is it is assumed that you can connect to Sockeye for this session. One thing is, for the GPU course, there's not going to be much, if any, hands-on. It's going to be a lot of general concepts and theory to get you primed for GPU. But for the future sessions this afternoon, tomorrow with software installation, tomorrow running jobs, and on, it is good to be able to access Sockeye and follow along as much as possible. If you have not connected with Sockeye or are having any issues connecting to Sockeye, we encourage you to check out the OSF link here or reach out to one of us. And lastly, I promise with the housekeeping, is we want your feedback. So time will be given towards the end of the session to complete a very short feedback form. For those of you on Zoom, you'll be prompted online. And for those of you in person, if you're willing to navigate to the the Open Science Framework page, at the link provided, we have a link to the survey there. So it's very short. It's not meant to be super intensive, and any feedback you have, good or bad, can help us to continue to improve our courses. The way today is going to look, we have 2 hours scheduled. We have 2 hours scheduled for all courses at the bootcamp. We don't expect to use that much time, although we're more than happy to keep you here for that long. I'd like to take a break about 50 minutes in. So for those of you on the academic teaching schedule for the Monday, Wednesday, Friday, we'll do kind of a 9 to 9:50, give you a break around there, and then come back with however much material we have left. Feel free to ask any questions at any time, or stick around and ask us any questions at the break or post-session. So what are we looking to cover today? We're going to get into a technical review of CPU and GPU architecture, performance and use cases, describe the GPUs that are available to you on Sockeye, describe installing software for use with GPU on Sockeye, review the GPU job submission, and describe and demonstrate how to monitor and review GPU jobs. This is pretty critical, and we'll spend a little bit more time on this towards the end. And it's really something that's applicable to all types of running jobs at on Sockeye, which can really be a benefit to your research. The last thing we'll talk about is some considerations for addressing low GPU utilization and common bottlenecks. Something we see with new users to GPU and many on Sockeye. GPU is not something that's easy to learn. HPC in itself can have a steep learning curve, and GPU even more so. So one thing to kind of expand on from the session objectives, what this session isn't, we're not going to get into coding here. So we won't be doing any sort of deep dives into PyTorch, C, TensorFlow, and we're also not going to be going into multi-GPU instruction. We'll talk a little bit about some considerations when using multi-GPU, but what we really want to cover is, one, what GPUs are and when to use them, as well as some real concepts to get you an understanding of some considerations when applying GPUs to your research. Because while there's I guess simply put, there's a lot that can be covered with GPU coding. We can get really into the weeds with C, C++, Fortran. We can get into some of the machine learning frameworks with PyTorch and TensorFlow. There's too much for 2 hours, and each of those really deserve a deep dive into them unto themselves. So what we're really hoping here is to help you with a mental model to be able to apply to whatever sort of GPU frameworks you're using. And then the other really big thing I think we hope you take away from this is, again, the monitoring and reviewing GPU jobs, and being able to improve your GPU utilization and use on Sockeye. One thing that I don't really have in this slide is, as part of this week-long boot camp, this GPU course does come ahead of 2 other courses, which kind of serve as a primer or can help with some of the understanding of GPU use. Those will be the software installation this afternoon, as well as the running jobs tomorrow. Where we might jump ahead a little bit if this is all new to you, I'll try to back up with a brief primer, but I would also encourage you to attend this afternoon and tomorrow morning sessions to help fill in some of the gaps. And if there is anything that you're getting stuck on, feel free to ask, even if it's not related to GPU. The one other thing, because GPUs, as you'll see, is really ideal for highly parallel computing. We're also going to have a parallel computing introduction tomorrow afternoon, and so that should also be a nice complement to our GPU course today. So with that said, let's start with our technical review. We just had a session objectives. We'll try to give you a bit of a section objective just to keep things on track, and so you don't get lost and I don't get lost. The key terms, we'll touch on some that you need to know, review the CPU and GPU architecture here, compare and contrast the relative performance and strengths of each, as well as provide some examples of CPU and GPU use cases. And then the one other thing we'll touch on very briefly is CUDA. CUDA is sort of this amorphous term, and I find often if you Google CUDA, you say CUDA is CUDA something or other. So it doesn't really expand on it or tell you what it is. Now, some might say, if any of you have looked at other GPU courses, some of them can go from 0 to 60 very quickly, especially when they introduce programming on GPUs involving C or C++. This course is going to be a little bit more basic than that. I hope it's not too basic for some, but I really want to build that sort of conceptual understanding before we move into, or before you move into working on with GPUs in your own research. So we're going to see some of that simplicity here. There's certainly a lot more terms that we can get into here, but I think there's a few key high-level definitions that we can briefly touch on. I know, Nick, if you attended our Introduction to Sockeye yesterday, touched on a few things, but related to the above terms. For example, the CPU is the central processing unit. That's sort of the brain of your computer, the main processor. So responsible for the logic, input, output, various computations and communications. It's really sort of the central, as the name suggests, the central unit. The GPU is the graphics processing unit. It was originally designed for graphics and video rendering, and we'll see why that's more critical in a few moments here. The one other thing, this is kind of a weird term that doesn't really fit in, but I'm just going to drop this in as a bit of a primer. That's the PCI bus. Peripheral component interconnect, I wouldn't really worry about that, but mainly the PCI bus or other like things are communication links connecting various computer hardware together to enable data transfer between them. And we'll see why that's important, especially as it comes to GPU computing. Two other terms, which we'll also talk a little bit about here, but also you'll see a lot coming up in working with GPUs, is the host and the device. The host typically refers to the GPU, or sorry, the CPU and its memory, whereas the device refers to the GPU and its memory. I have a little star over device because this isn't 100% true. So for example, if you're working with a language like PyTorch, you may have something where you set the device to either your GPU or CPU. So to set it to CUDA, which we'll come to shortly, or your CPU, depending on whether or not CUDA or GPU is available. So in this case, device can be two different things, but typically the host is the CPU and its memory, whereas the device is the GPU and its memory. The one other thing we'll talk, I might reference briefly, is the kernel. In GPU programming, that's a function or program to be executed on a GPU. If you were to get much more into the weeds with C, C++ programming, that's going to be a lot more, I think, critical to using a GPU. But for some of the higher level languages where that's abstracted away, it can be helpful to understand the term and potential lag in a program starting or firing up as the kernel starts. But it's not necessarily something you need to consider. You'll see maybe in other courses, there's discussion with GPU threads and blocks, SMs or computing units. So different GPUs from different chip manufacturers have different terms. I've tried to stick to some of the commonly agreed upon terms and not get into too far into the weeds with some of them. So we're just going to stick at this high level for our conceptual understanding. So again, a very simplified diagram looking at the architecture of the CPU and the GPU. From what you can see of the CPU, it's made up of multiple cores. Your standard desktop computer may have 6 to 8. A really high-powered workstation might have 16 to 24. These can be, these are typically bigger, beefier cores, well suited to serial computations. The CPU, again, is responsible for mathematical computations, logical calculations, running code, communicating between different components of your computer. And one thing that we'll see shortly is a bit of a primer, communicating with the GPU itself. One critical thing is a CPU core itself can handle one task at a time. They're very well suited to serial work. CPUs, as we'll talk about a little bit later in this session, and more so in the parallel programming session, can conduct work in parallel, but it happens a little bit different than how we would do so in the GPU. One thing I'll talk about here briefly is the CPU cache. This is similar to your random access memory or RAM. However, it's a small bit of memory that's closer to the CPU cores that is a short-term storage for CPU calculations that the CPU might need, for data that the CPU might need to access very frequently and very recently. I just want to throw that out there because the cache is referenced here. But what we're really going to be focusing on is the fact that CPU is good for sequential operations, good beefy cores, and not a huge number of cores. It also has access to your system memory, so your RAM. The GPU, as you can see here, has hundreds of cores, or in the case of, went the wrong way. In the case of some GPUs, even thousands of cores. So this diagram here is a little bit simple. Our GPUs, which we'll discuss a little bit further down the course, have upwards of 5,000, I can't remember the exact number, but about 5,000 CUDA cores. So it really allows massive parallel operations. And the GPU can be thought of as an accelerator that works in concert with the CPU to perform certain tasks. The GPU, as a graphics processing unit, was originally designed, as the name implies, for graphics rendering, which has a highly parallel and mostly independent style of computation. When you think of the graphics rendering, outputting streams of colored input or pixels on your computer, these can all happen independently of each other from independent sources. So when you think of how that can be applied to HPC, you can start thinking of various works that can take advantage of independent, highly parallel applications. And we'll talk about some use cases shortly. The one important thing to note is just because a GPU has hundreds or thousands of cores compared to 4, 8, 16, 32 of a CPU, once you get over the equivalent number of CPU, it doesn't necessarily mean that you should run on a GPU. A GPU isn't well suited to all tasks that may be better suited to a CPU. So at a very high level, again, going through a bit of a conceptual understanding, I need to include the hyperlink of that because there's this was presented by NVIDIA, a man named Stephen Jones, and he does a very good job of explaining CUDA at a little higher level. But I think this provides a nice sort of visualization or conceptualization of what a GPU can do in terms of processing without getting into some of the terms. So you can see some of the terms I didn't touch on here, blocks and threads, and we'll touch a little bit, or it may touch a little bit on computing units. It's more important just to focus on the figure itself. So if you're looking at something like image processing, an image can really be broken up into many small fragments, and that image can be processed, or the fragments of that image can be processed independently of each other image. So what you can actually do is take that image, break it up into smaller units, and then allocate those little blocks or fragments of the image onto your GPU and run a similar sort of set of computation on each image. And that's kind of how GPU processing works at a very high level. One thing that I've kind of mentioned, though, is the CPU and GPU communication. So the CPU is responsible for really the high-level operations and most of the operations in your computer. The GPU, you want to run code on a GPU, you want to perform your PyTorch, your TensorFlow. It's not just a matter of writing some code and then having it run on the GPU. It has to get to the GPU somehow. And this is where the PCI bus comes in, and this is where we can actually see quite a bit of latency with a GPU job. So the CPU has access to the CPU RAM, the CPU being the host and the computer's RAM being the host RAM. The GPU has its own RAM, which we'll touch on a little bit with the Sockeye architecture. This RAM is typically a lot smaller than what's available on your computer. So what we'll see on Sockeye is we have GPUs with 16 gigabytes or 32 gigabytes of GPU RAM. While smaller, it's very high performant. But the important thing here to note is you need to be able to load your work onto the GPU memory for the GPU to carry out its computation. So we kind of talked about that briefly here. CPU and GPU, they're not really standalone things. You don't just run a job on a GPU. You don't just run a job on a CPU. I mean, you can do if you're not using GPU, but really CPU and GPU are really function and compute as a team. And it's really important to understand and remember that when you're planning your job, when you're writing your script. And what I mean from that is, regardless of the high level or low level programming language you're using, whether you're using something like C and really allocating data to certain blocks for computing on your GPU, or whether you're using something a little more high level like a PyTorch that abstracts something away, it's important to consider that your program always starts on the CPU. The CPU or the GPU to perform the analysis copies data to the GPU. The GPU then performs some sort of analysis with instructions from the CPU, and then the results are copied back from the GPU to the CPU. So one of the things I talked about before, which we'll talk about a little bit further down the line with discussion about improving your utilization, is thinking about where some of the lag or the latency may be introduced. And that can be frequent copies back and forth between the CPU and the GPU. We'll also talk about a few other things related to this, but it is important to conceptualize as you write your code. Your program starts on the CPU, you're copying to the GPU with instructions, running on the GPU and copying back to the CPU. Another thing to note here is, well, perhaps that's it. I think I've covered everything I want to talk about there. Okay, so kind of a summary of the relative strengths of a CPU and a GPU. CPUs are made up of several cores. They're much faster when handling different types of system operations. So some RAM or random access memory computations, mid-range, and can handle computational depth and complexity more readily. They do have more of a cache memory, than GPUs, which I touched on briefly. So they're good at handling a larger set of linear instructions. They have a lower latency and are good for serial processing. So very sequential, stepwise jobs or following instructions. A GPU has, as I mentioned, hundreds of thousands of cores. They're really designed for high throughput and mostly independent parallel processing, working on breaking something down and working on many, many pieces of that whole with the same set of instructions. And so if you're thinking conceptually about what you might be using a GPU for, you can think of things like image processing, as I touched on, simulations where you're running an algorithm multiple times on the same input data, machine learning where you're working with neural networks, training models, again, when you're running something multiple times with the same input set of data. And the really big advantage here is they can do thousands of operations at once. That's actually the same slide, so I'm going to leave that. So one other thing to touch on here is something you're going to hear about whether you're working with GPUs on your own computer or in particular when you're working with GPUs on Sockeye is CUDA. What is CUDA? CUDA stands for Compute Unified Device Architecture. Is that helpful? Probably not so much. If you Google what is CUDA, you're again probably not going to find a lot of help because it's going to say CUDA is this, and it doesn't necessarily get into a real deep understanding, or you'll see something along the lines of the definition I've provided up top. It's a parallel computing platform and programming model that enables software to use NVIDIA, and I'll touch on the bolded NVIDIA in a moment, GPUs. So I think the easiest way to think of CUDA is it's embedded in the hardware, and it's also software. It's an API interface, and it's many things. Really what it allows you to do, to think of at a very sort of basic or rudimentary level, is CUDA allows your program to use the GPU for some sort of computing. And so various apps and frameworks in the second table here, TensorFlow, PyTorch being the two most popular, take advantage of CUDA. There's a number of other machine learning CUDA libraries that can be used. You can use a bit more low-level languages with CUDA C++, the CUDA compiler, and there's also Python libraries that can take advantage of CUDA. So if you want to use something like NumPy, a GPU-enabled NumPy, that's also available. And then there's an additional 600 plus other GPU accelerated applications. This would include ANSYS Fluent, Gaussian or GROMACS, LS-DYNA, OpenFOAM. Many of these we have available on Sockeye for use as pre-installed modules. And if it's something that you're looking to install to use on Sockeye as well, we can certainly help you get it on board. A few others, which actually aren't included here, which I'll bring up, that is available on Sockeye would be LAMPS, or large-scale atomic molecular massively parallel simulator. Hopefully everyone's got that. I'm sure the LAMPS users do, and I think that's the important thing. LAMPS is available for use on Sockeye. It's a software application designed for molecular dynamics simulations. So for those here that aren't going to use it, at least there's an understanding of what it's used for. And as a piece of simulation software, it's well suited to GPU. One other thing I do want to touch on briefly, for those that may not use Sockeye, for those that may be using other HPC systems with partners, or looking to use GPUs in the cloud, there are other GPUs from other manufacturers out there. One of them would be AMD GPUs. Their somewhat equivalent of CUDA would be the Radeon Open Compute module, I believe is the M. And that's ROCm, an open source platform. One of the advantages of it is it includes tools for porting to CUDA code. There is a bit of a learning curve getting familiar with CUDA versus AMD and ROCm, but that's certainly something we can help you with. And Jacob, who's in the room, has been working with some of the UBC researchers, enabling their work on AMD GPUs. So I don't know if Jacob wants to touch on anything now, or if anyone has any questions about AMD GPUs, I'll throw Jacob under the bus, and I'm sure he'd be happy to work with you about them. Perfect. Okay, so with that, we'll take a brief pause, and I know we covered a lot of technical information. It is kind of, maybe it's basic for some, it's probably not going to be basic for others, but I wanted to find that happy medium where you can start to get a bit of a framework for thinking about how to consider the use of GPUs when you're writing your code. So I'll pause there briefly. I'm also going to grab a water, and I'll be back in about 20 seconds. It's not our actual break yet. Okay, we're back. So we get a little bit lighter, maybe for some, maybe not lighter for some others. For the next few minutes here, leading up to our break, we're going to talk briefly about GPUs on Sockeye. So what are we really looking at here? Not much, just to describe the GPUs available to people on Sockeye. I'm going to throw this slide up. There's a lot here. I want you to note, before we talk about the node specifications, before we talk about anything else, I want to discuss one of the links which isn't highlighted, just under the table on the bottom right, adapted from HTTPS Confluence. What this links to is our technical user documentation for Sockeye. There's also information on Chinook, Globus, file transfer. Everything that we discuss in these courses is up there. There's also a lot of technical information on Sockeye and our other systems. So while we're here to help, we want to work with you as much as possible. There's no such thing as a stupid question. And please reach out to us anytime you need help. I want to put all that out there first because I don't want to discourage anyone from reaching out. We do also encourage you very strongly to read the docs. We have also in the room, Michael, Eliza, they're two of our document authors extraordinaire. Our systems team has authored quite a few documents, as well as Jacob. So there is quite a bit of really good information there, as well as this table, including more than just GPU. So we do encourage you to reach out to us, but also read the docs. And if there's anything you get stuck on there, anything you have questions on, anything that we can do to improve on those documents, please let us know. And oftentimes, or in many cases, if you have a question about something, we will happily answer your question through our ticket queue, arc.support@ubc.ca, but we will also often provide a link to the documentation to help you strengthen your understanding or provide a deeper reference. So with that little disclaimer out of the way, we'll talk about the GPUs that are available on Sockeye. We have a total of 200 GPUs across 50 nodes. 44 of those nodes contain 32 GB RAM GPUs. So as I talked about in that very rudimentary architecture slide earlier, those GPUs have 32 GB of GPU memory. We have an additional 6 nodes with 16 GB of memory. One of those 16 GPU nodes is set aside for the interactive GPU queue. What that means is, and we haven't really touched on running jobs yet, Nick introduced it in the running jobs section, or sorry, in the introduction to Sockeye yesterday. But if you're not familiar with running jobs on Sockeye, there's mainly 2 ways to do it. The main way is to submit a job with what we call a job script. This sends the instructions to the system, to Sockeye, that you want to run. So I want to run this script for this amount of time with these resources. That's how you would submit, or that's how you would work with 49 of these GPU nodes. The other one, the interactive GPU, actually allows you to interactively work in it with a GPU. So that would be similar to those of you interactively working on a Jupyter notebook, although you're doing it on a command line here, or an IPython kernel. It's interactive. Whereas the other side, the other 49, you submit this job, you set and forget. You're running a script, and then you're leaving it and coming back to it when it's finished to review the results. The important thing is the interactive GPU, there's only 4 GPUs in this node. All GPU nodes are comprised of 4 GPUs each. And that's the same with the interactive GPU. It can be quite popular. The main thing we encourage for use with the interactive GPU is maybe some profiling in some sections, some troubleshooting, some debugging to be able to then submit your job to the batch system to run. The interactive GPU only runs, we've set some limits there, and I believe the wall time limit, the amount of time you can request for your GPU to run with the interactive queue, is only 3 hours. So with only 4 GPUs and 3 hours of wall time, it can be in high demand. We encourage you to, as I said, use it sparingly, but really take advantage of our batch system. Oh yeah.
That means really 4 people can use the interactive GPU session at once because it's 4 cores, or maybe 2 people who choose 2 cores?
That's a great question. So I believe you could have 2 people using 2 GPUs each, or you could have 4 using 1. Yeah, it's because you can have a maximum of 2 running, and then or you can have any combination thereof, adding up to 4 with a maximum of 2. So 2 1 1 2 2. Yeah.
Jeff?
There are. Oh, sorry.
Is it possible you could repeat the question? I think there may be a value for online audience to hear that.
Oh, thanks, George. So what the question was, is it how many people can use, and I guess the simplest way to re-put it would be how many people can use the interactive GPU at a time. A maximum of 4 could use it at a time with 1 GPU each, although you could have 2 users using 2 GPUs each, or user using 2 and then 2 using 1. If the GPU queue is booked up, then you will just have to wait until your turn is available. Yep, question.
I'm probably just really confused, but I thought that one of the big advantages of the GPU is that you have thousands of cores. And maybe I'm misinterpreting the table, but I only see like 24 cores. So where do we get to the 5,000?
Oh, okay, that's a great question. That's a great question. So we have, I'll run through the table from left to right, and then that will, I think the nodes is somewhat self-explanatory. We have 50 GPU nodes of X types. Each node has the corresponding CPUs available, and then the number of cores is the CPU cores. So those are the total CPU cores. We don't discuss the, or we don't put in the number of cores on the far right corresponding to the GPU. So the GPU has, I believe, about 600 tensor cores and 5,000 CUDA cores. Really here, we're talking about the CPU cores, the computing units. And one of the things, and I think jumping off that great question, is one of the things that to consider when you are running your job is when you're working with 1 GPU, you typically don't want to request more than 6 cores, thinking of there's 4 GPUs to 24 CPU cores. Once you start to get into over 6 CPUs per GPU, then you could be hogging resources from other people sharing that GPU node and impacting the ability to run jobs. So usually it's a good practice to request 6 or fewer cores per GPU. And if you are curious, there is a high level of technical information on the Tesla V100s at the NVIDIA link below. Okay, any other questions on this before we move on? Just a very high level, brief overview of our GPU nodes. We're actually going to reference back to some of this when we talk about running jobs, but I really wanted to call attention to our documentation, to our interactive GPU limits. And when we talk about software in the running job course, we're actually going to get a lot more into considerations around job limits, scheduling, resource requests, and that sort of thing. So this will be more critical in later sections. So briefly, we're going to touch on software for GPU jobs. Jerry, this afternoon, if you're attending the software installation, is going to do more of a deeper dive into software installation on Sockeye. This will be applicable to software for GPU. So we're not going to do too much of a deep dive here, but I do want to provide a bit of a high level overview of ways and best practices for installing software on Sockeye to use. So touching on that, we're going to review how to load or install software for GPU jobs. And then again, see Jerry's course this afternoon or review his slides on the OSF link here. So not to get it too far ahead of ourselves and not to get too outside of the GPU focus today, a lot of software is available pre-installed as modules on Sockeye. So what this means is certain things you want to run Python, set up a virtual environment, work with lamps, use Conda to install your tools, use a Singularity container, which we'll touch on briefly. These are all available on Sockeye, ready for you to use as modules. These are the commands Jerry will get more into this afternoon, but what you can do at a high level is list the modules that you're using that are currently active in your Sockeye allocation. You can search for modules, you can load them, and you can create saved module environments to use. So this takes a lot of the the installation headaches out of various programs and allows you to get up and running much faster. And again, I'm not going to spend too much time on this. If you're really stuck on something, feel free to ask us, but there will be a lot more information on it this afternoon. Some pre-installed software modules we have available on Sockeye would include LAMPS, GROMACS, Fortran, which can all take advantage of GPUs. Other software, including commercial software, may be installed upon request. Please reach out to us through arc.support, and we'd be happy to work with you on it. One important thing to note is a license might be required, especially a paid license, and there might be some back-end system administration to ensure that license is accessible on Sockeye and the software can be run on Sockeye. So if you're unsure, please reach out to us and we can work with you. But we may need, and for some software, we may need to work with you to ensure that license is active on Sockeye. ARC does its best to make UBC purchased enterprise purchase licenses available on Sockeye, but there may be some cases where it isn't, and we'd have to work with you to bring your own, especially if there's a cost. As far as other software installation methods, virtual environments is a big one. This is really ideal for PyTorch and TensorFlow. We have in the past installed modules for each. One of the things, or one of the big hangups with that is we have people using many different versions of PyTorch and TensorFlow, and we can't hit them all. People are still using versions 1.13, 1.15 of TensorFlow, and many iterations of the version 2. So what we would recommend is virtual environments or containers, which we'll talk about in just a moment. Depending on the version, you need to be aware of the GPU or CUDA version you're using. Virtual environments can often take advantage of this. The second bullet point is something I really want to emphasize. Many of our users are on both Sockeye and Compute Canada, or now Alliance, Digital Research Alliance of Canada systems. On those systems, because it is a shared resource across Canada with many thousands of researchers, the Conda is not permitted. Conda generates, put it kind of bluntly, an insane amount of files, and it can create a lot of stress on the system, especially when you have many users. So on the Alliance, Conda is not permitted. It is on Sockeye. We would encourage using environments such as PyVirtualEnv as opposed to Conda. It is quite straightforward to install. PyTorch, for example, or we would encourage you to use a Singularity container. Again, we'll touch more on Conda and virtual env in this afternoon session, but I do want to highlight that these are more ideal for things like PyTorch and TensorFlow. Touching briefly on getting the appropriate version for each, I would suggest you follow the links here to review the versions that you need of Python, CUDA or CUDA toolkit, etc., and to ensure that there's no dependency issues or I'm trying to think of the word. I'm blanking on the word. To ensure that there's no conflicts is the word I was thinking of. The last one that we'd also recommend, especially because it's useful on basically porting anywhere. If you have a container, you can work it on Sockeye, you can work it on the Alliance system, you can work it on the cloud. It really enables portability and reproducibility in your research. Many Docker and Singularity container repository options are available. One key thing to note is Singularity is the HPC specific container option. So if you're working on HPC systems such as Sockeye or the cloud, or Compute Canada, the Alliance, you are going to need to use Singularity. That said, with Singularity, you can pull Docker containers. One thing we recommend for many types of GPU-enabled software is the NVIDIA NGC catalog or registry. This is an NVIDIA supported registry of basically a ton of GPU optimized containers, PyTorch, TensorFlow, many others. These are, as mentioned, these are optimized for use on GPU, makes installation very easy. Jerry again will touch on that, but you pull the container and you run from there. You can run these containers with our Jupyter notebook set up on Sockeye if you're looking for something interactive, or you can submit these to run in our as a regular batch job. One consideration or highlight that I will note is you do need to add the NV flag with Singularity exec run commands to make sure the container can access your system's CUDA and the GPU. I'll have a little note on this when we talk about the GPU software script or the GPU job script, as well as we reference this in our technical user documentation. I think we're just at about 50 minutes, which is great. So if there's any questions here, I'll take them now. But otherwise, we'll take maybe a 10-minute break. We'll come back on the top of the hour and we'll start with running GPU jobs. And then I think getting into something really important for many of you, monitoring, reviewing, troubleshooting your jobs, and considering some best practices around utilization.
I'm probably really lost here.
Yep.
I don't think you ever told us what a container is. Is that like a pre-installed package that you just drop there and everything's ready for you? I don't understand.
Yeah, no, it's a great question. And yeah, I apologize. I kind of glossed over it because we're reserving it for. So for those online that haven't ducked off to take a break, the question was, what is a container? The container is, it's kind of a self-contained environment or thing with its own operating system, with its own software, its own binaries or executables. So really it's kind of like and this is not entirely correct, but you can think of it, conceptualize it this way. It's almost like a little system running within a parent system or a host system. So if you have certain dependency issues, like if you want to run on a Linux machine, Sockeye uses CentOS 7 Linux. We have various packages, binary software installed. If those don't work for your container, or if those don't work for the program you're using, what you can do is install a container, which is a self-contained operating system environment, which can take advantage of the computing resources within that system, but really it allows for its own dependencies, software configuration to ensure that there's no conflicts what you're using. Now, in some cases, you may be using the same sort of configuration or setup as what's currently on your system, but the nice thing is you can run that container on different systems where you may not have that same compatibility.
So just to see if I understand,
Yep.
if there's a software that I wanted to run and I know it's included in a container, then I wouldn't have to install anything. I would just run it in that container and would make my life a lot easier.
It certainly can. Yeah, it absolutely can. So what you would need to do is the containers or Singularity containers, what they exist at in a Linux platform is a file called a CIF file. And what you can do is you can execute or run that container and run whatever command, whatever software you want to that exists within that container. So if you don't want to install something that's not there, what you just have to do is download the container file and then run the container command to execute that software. So in many cases, it can make your life a lot easier, especially if that software isn't available on Sockeye, it isn't compatible on Sockeye or easily installed. If you don't want to mess with a really messy Conda installation, or you don't need to add anything extra. You have a container with everything you already need. I don't know if Jerry or Jacob would like to add anything further to that, or if I butchered anything.
One really good thing about containers is because it's a single file and it's independent of what the system is. Once you have your container set up with your environment, you can copy it to any other system that
run Singularity and it will run the exact same way. So you don't have to worry about basically what the underlying operating system is. And it also gives the good benefit of if you have somebody who'd like to duplicate your research, rather than having to explain to them how to set up the environment that you did, you can just say, here is a container file, run the container with these commands, and everything's good to go.
Since this is more of like just like a general question, so more Singularity is more of like a PPC thing. Is there a possibility of getting Singularity on a personal workstation as well, so that I can like kind of sync up and so instead of like, because right now what's happening on my computer, I have Conda. That's why I'm like I'm helping with getting Conda to work on Sockeye, but now I realize that maybe Singularity is the better way, so I put it the other way around. Is I learn Singularity and use it on my computer.
Yeah, that's absolutely an option. You can. So it also raises a really good point that I think Jerry will touch on this afternoon. So for those in the room, virtual room, listening to questions, the question was, can I install Singularity on my local computer and work with it there? The answer is yes. And doing so actually gives you some advantages. In some cases, with a Singularity container, you might be able to pull one from a repository that has all of what you need, or you might be able to pull a very basic vanilla container. So maybe just a container that has the Ubuntu operating system and you put everything else you need. And maybe the NGC catalog, you can install one with PyTorch, TensorFlow, maybe there's some libraries or something you're missing. If you're installing containers on Sockeye, you don't have the ability to modify that container because as a Sockeye user, you don't have root access. If we gave users root access, bad things could potentially happen. It's very easy to abuse the system, now not purposefully or maliciously, but when you have root, you can really run amok. So Singularity on Sockeye, there's less flexibility to do something with that container. We do discuss in the software installation some workarounds for that on Sockeye, but you can certainly install Singularity on your local machine. There are some caveats around doing so. So depending on your operating system and how you would have to work with the container. But the nice thing with that is you can modify that container if you'd like. So if there's something else you need to install in it, you can do so. You basically open the container, edit it, create a new CIF file or container file, and then save that to Sockeye or elsewhere. Yeah. And we'll touch a bit on that. It is like other HPC things, I suppose. There is more, or HPC adjacent, there is a bit of a learning curve on that, but we are also looking at putting in more of a Singularity deep dive session down the road, either this fall or this winter at some point. No problem. I'm gonna run out the washroom quickly.
So one of the reasons I might also be interested in, I'm very basic, but there's I'm an evolutionary medicine and there's this population genetics program called BAG for stuff model. And so recently there was this new version. Because when it started to make it very confusing. And so it apparently uses GPU computing. And so all I can glean from here is that it's so how would I go to? Yes, how would I go about finding out if I could run this on something?
From what it looks like, it's using PyCUDA and CycleCUDA, which are both Python-based libraries. It's focused on Sockeye. You know, that use CUDA-based implementations. The learning side, you have people use Python for PyTorch TensorFlow. So in this case, what you need to do is you need to get access to whatever the algorithm software is, whether that is kind of a Python library or it's basically here here's the code that I worked with using needs libraries. And then from that, basically you can set up an environment for you, or you can set up an environment that has all the dependencies and run just that Python script.
Okay, so, yes, so I think you touched on what I wanted to know. So, I mean, so I usually do a lot of work in computing, and until recently, they used to be an administrator that would, doing this in developing software. And now you get to install software, and I always try to follow through that. I mean, I can run some code for things that. So you guys could provide that kind of support.
If you like to install something on Sockeye, it's something with kind of doing software, that's the way we need it. Or you kind of have all the instructions on, here's how to install it, here's all the framework, but I don't know how to do this on Sockeye. You can contact our support and we can help you basically get a set for that's either building a virtual environment for your system for your own use. We can help you with building a container that you can use between systems, or if it's just kind of if it's something that we think might be beneficial to everyone in Sockeye, we could look at and building up the basic things to like a module. But okay, this seems a little specialized, so it's probably going to be just for maybe your project. But in that case, yes, we could certainly help you either.
Okay, great, thank you.
Okay, welcome back, everyone. I think we're at the top of the hour, so let's get this party going again. So I think the two main things that people might be interested in, new and experienced users, is running GPU jobs and monitoring troubleshooting jobs. So that's what we'll get into here, actually using or working with a job on Sockeye. Some of this is a little bit, some of the running GPU jobs section we're going to talk about here is maybe a little bit more basic for some, but there's a few things that do trip people up. So we're going to kind of just cover everything. Bear with me. Well, what I'd like to review in this section is some of the job script requirements for GPU jobs. Again, we're discussing running jobs, this job script in a meatier section tomorrow. So I'll try to cover sort of the high level idea of what we're doing, but also please join us tomorrow morning. And we're going to review the general procedure for running jobs on Sockeye. I should have flipped this. That's actually first because I do. It's not there. That's interesting. Okay. We'll get to, I think I will talk about that. Oh, I put it at the end. That's why. Sorry, I've got a different slide deck. Okay. So the GPU job script or the job script generally. This is what it looks like. If this is familiar to you, great. Maybe you can tune out for a minute and I'll just try to yell if there's something you should key on. Otherwise, for those of you that are new to Sockeye, this is the file or what a screenshot of the file looks like for you to interact with the main workhorse of Sockeye, the CPU, or sorry, the compute nodes. So you submit what's called a job script, this script here, with your instructions to run your analysis, whatever that may look like. The top here, these hash PBS are the directives or instructions you're giving to the scheduler to give to the system to decide what to schedule your job with the set of instructions. I think I kind of said something fairly circular there, but the PBS directives at the top, I'll say it again, are the directives or instructions given to run your job. So the very top one, I think Nick mentioned yesterday, are the resources you're requesting. So the wall time is the amount of time you'd like your job to run. That's not necessarily how long your job will run for. So in many cases, we see jobs run much faster than what's requested. That's great. What we'll talk about a little later and talk about tomorrow is if you're requesting a really massive wall time and your job's finishing really quickly, it's usually good practice to adjust it down. The select is the number of nodes you'd like. The N CPUs is the number of CPUs. N GPUs is the number of GPUs you'd like to request. I'm going to touch on it here. As I said, we're not really talking about multi-GPUs today. Of course, you can request more than one GPU. We're sort of touching on one GPU. Really, it's a good practice, unless you're an experienced GPU user, to start with one GPU. You have 16 or 32 GB of GPU memory, which we'll talk about. Our GPUs are pretty powerful to be able to run many jobs on one GPU. The important thing is often to start with that one, see how you're doing, and then once you have good memory usage, good GPU utilization, or you find that you're not getting enough power after that, then it's good to start looking at using multiple GPUs. That's something we can help you with, that we're looking at providing a future course on multiple GPU computing. But right now, it's usually good practice to start with one and go from there. This statement here is optional in our technical user documentation. This isn't included in our standard GPU job script. You can request a 16 GB or 32 GB MEM GPU type. Most people are not going to specify 16 unless they really need it. If you recall, there's far fewer 16 GB GPU nodes. So if you request that, you're really going to be limited. Even if you request a 32 specifically, you're going to be limited. You're going to lose the ability to use those 16 GB nodes or GPUs. The important thing here to know is if you don't need it, unless you're sure you need more than 16 GB of memory, don't include this, because then you open up your ability to use any of the GPU nodes. The other thing is, if you do put a value not equal to 16 or 32, so one common one we've seen is 64, your job will never run. We'll talk about how to troubleshoot and monitor your job a little further down the road, because we do hear from people, why isn't my job running? And if you look into your job script or your monitor your jobs with a few different ways or a few different methods, you can see actually there's often information telling you why your job isn't running. When you're submitting a job, you do need to append the GPU suffix to your allocation code. We'll talk about that more tomorrow, but this ensures your job is directed to the GPU queues. We talked about CUDA earlier. You do need to load the CUDA module to enable GPU usage. And then it's typically good practice to request no more than 6 CPUs per GPU. The one other thing I'll touch on here again as a reminder is if you are running a Singularity container, include the NV flag, that -- NV to ensure CUDA GPUs are available to your container. This is something that we've seen trip people up with the Jupyter data science.pbs job script. For those that are using GPUs with our Jupyter notebooks on Sockeye, we do have a little note suggesting or requiring you to add this if you'd like to use GPUs in those notebooks. But I do want to highlight it in here again, just because it is something that's easy for people to miss. And again, this is kind of a real flash through the GPU job script. So we'll talk about the job script more generally tomorrow, but I did want to highlight a few of the key considerations with the GPU script. Generally speaking, though, and I do want to talk about running jobs on Sockeye generally, because there is something that we do often see, and I'm not shaming anyone. We're all guilty of this. I've been guilty of this in the past. How do people often consider running jobs on Sockeye? There might be some planning, there may be some resource estimation. Maybe you're completely new and you have no idea how to estimate resources. That's fine. There's nothing wrong with that. You have to start somewhere. Maybe you're going to throw something at the wall and see what sticks. Maybe you find a job script where your job runs for you and that's great. So you're going to keep using that. So what often happens next is we get this feedback loop where you submit your job runs, maybe your job fails, and you're just going to use that to submit new jobs, or you're going to tweak something slightly and you're just going to resubmit that job. The thing you're not necessarily looking at, though, is my job running efficiently? And I guess from that, could it be running more efficiently? And what can I do to make it better? Part of that is so you're not waiting in the queue as long. And part of that is also being a good HPC citizen so that you're sharing, ensuring resources are well shared with other users on Sockeye. But from a pure selfish standpoint, which you all may care about, I want my job to run as soon as possible. I'm impatient. What can I do to get it to run faster? And so really, this is kind of what you should be considering anytime you're running a job, GPU or otherwise, is plan your job, write your jobs, write your analysis script, write your job script to feed to the submission, submit that job. You can actively monitor it if you like. That's a nice handy tool. We'll talk a little bit about that shortly. But then after your job is complete, at minimum, it's always good to look at the job performance analysis. We're going to talk a little bit about some GPU specifics here, but we're also going to spend a lot more time tomorrow on job performance analysis, because this is where you can really improve your own HPC usage by being able to modify and continuously improve your utilization. And then from there, you can revisit and modify your request. Either we'll go way back to planning or back into the job submission, depending on how you conceptualize things. So this is kind of a really nice conceptual way to think about how to approach running a job on Sockeye, whether it's a GPU or otherwise. Any questions about sort of the high level overview, GPU job script, running job generally? As I said, we're not really going to get into running GPU jobs today. There's many different ways we can do it. And I find if I'm giving you jobs to run, I could give you something kind of a hello world on C, or I could give you a basic PyTorch model. That's not necessarily going to help you because the code may not be applicable to you and it won't necessarily help your understanding. I am going to try my hand at a live demo of something. If it doesn't work, I do have a little backup, kind of like the flash forward when you're doing a cooking demonstration where the food's already cooked. I can pull it out of the oven, but we'll try running a live demo at least shortly.
Jeff, we do have a hand raise in the Zoom room.
Is someone able to?
They should be unmuted now.
Hi, can you hear me?
Yes, go ahead.
Perfect. This might be a silly question. I'm just getting a little confused with the difference between the nodes and the cores. And then when you're like submitting a job script, your selection of your nodes, like how does that relate to, I guess, the number of cores? I don't know. I'm just getting a bit tripped up with that, please.
Okay, no, it's a good question. So there's, I guess, I'll say there's no such thing as a silly question, only a silly answer. And I'll do my best not to do that. But I should pull up a diagram for that. There is something in the running jobs section. So what the HPC system itself, what it's, the way it's designed or architected is the computing units, the CPUs and the GPUs are separated into different nodes. So we have X number of nodes. I think it's 600 and something. I know Michael just did the calculation the other day, 400 or 600 nodes. Nodes on Sockeye.
Oh, yeah. Without GPU, I think it's about 410.
Okay, so we have about 410 compute nodes or nodes on Sockeye. What a node is a node is a group of either CPU or GPU or both units. So a node can be made up anywhere from 24 to 40 CPU cores. And then the GPU nodes, each GPU node is comprised of 4 GPUs. It would probably be a little bit easier to show a diagram of that. I don't really want to mess too much with Zoom to pull that up now, but I think it'll be better explained in the running jobs section. But you can think of a node as a cluster of CPU cores or a cluster of CPU cores and GPUs. So typically what you're often going to be doing, unless you're working with really, really massive jobs, is you're going to be working on a single node with a bunch of CPU cores, or you're going to be working on a single node with 1 to 4 GPUs. When you start to go beyond the node, then you're getting into some really massively parallel computations. So you need more CPU cores than a single node has to offer. If that's something you're looking at, we can certainly help you with that if you're unsure. And we'll discuss that a little bit more tomorrow in our parallel computing section. But just to jump back again, a node is a collection of CPUs and or GPUs, sort of at its basic. Does that help at all?
Yes, that was really clear. Thank you.
Perfect. Okay. Anyone else? Okay. So, second last section, doing okay for time. Reviewing GPU jobs. I think this is something many users care about. Many users maybe don't, but maybe should care about. And 3 really big questions you should always be asking. Not for GPUs, as I sort of touched on in the process for running jobs on Sockeye. 3 big questions you should always be asking when you're working on an HPC system. One, and I think we do often see the first one at least, because we do often hear, why isn't my job running? We can certainly help you with that, but we do also provide strategies to assess why your job may not be running, both here and in tomorrow's running job session, because you typically, if you don't know and you're panicked or you're frustrated, you submit a ticket to us. We'll get back to you as soon as possible. But then maybe by the time we do, your job's already running, or it's something that you could have quickly looked up on the system and then fixed and got your job running. So obviously a big question. We're certainly happy to help you with that, but we'd also like to enable or empower you to be able to do your best to assess why it isn't. The other one, of course, is how is my job doing? And so perhaps you do want to take that middle step in the running jobs where you want to monitor your job live. We'll talk about some GPU specific strategies here and some more general strategies tomorrow. They do overlap quite a bit. There's just a few separate GPU commands that we'll talk about. And the last one that you should really be asking yourself is, how did my job do? How is my CPU utilization? How much memory did I use? How much wall time did I use? I requested a week of wall time, 168 hours. I used 2. The system doesn't schedule your job based on what you use, because it doesn't know how much you're using until after the fact. It schedules your job based on what you request. The more you request, the harder it can be to schedule your job. So it's always good to review how your job did, improve, one, because I think it's beneficial to, I think, learn, grow, become a better user of the system and more in control of your programming and your analysis, but also just to get your jobs running faster on the system. So reviewing GPU jobs. This QStat command is one of the PBS commands, the portable batch system or scheduling system. We use a system now called OpenPBS. For those of you on the Alliance, you may be familiar with Slurm. These are PBS specific commands. The QStat command allows you to query information about the queues available on Sockeye. So when you're submitting your job, it's being submitted to a specific queue, or if you're not selecting that queue, it's being routed to a specific job queue to run. And that job queue or queue would be made up of different nodes with different number of cores or specifications. This is kind of loosely speaking, but if I'm submitting a GPU job, it's going to be submitted to the GPU queue. So the queue stat allows you to query various levels of the system as a whole. You can queue, or you can query the list of jobs you've submitted, and you can query job queues themselves to see who's running jobs in a specific queue, or who's finished running jobs in a specific queue. And you can also drill down into a specific job that you've run. So one good sort of quick command to see why your job may not be running is to use the QStat job ID modified with the -S option. What that does is, and for those of you that have followed along in Sockeye or familiar with Sockeye, this is what it looks like in your terminal. I'll try to get to a live demo shortly of a few of these things, but this is your output. You have your command QStat-S. There's my job ID there, 4103746. And then I can see in the comment here, not running insufficient amount of GPUs. So other users are taking up the GPUs available. My job's just not running yet because they're not available to me. Just have to be patient. Another command you might see, this is where some people get tripped up if they make an incorrect GPU mem request. You might see a comment, if you request GPU mem, for example, equals 64 GB, you might see job will never run, and then a comment basically saying request not equal to 16 or 32. So if you message us saying my job's not running, why isn't it running? This is one area where it may give you key information. One other minor thing we often see, or not often see, but do from time to time, and I know I've been guilty of it, is if you specify a memory request and forget the G. So if I put in 32B for bytes, that's going to impact your job's ability to run. So this is a nice sort of quick fire way to get the comment. Another way you can do this is with the -F option. This, I've only shown you the output for the last 8 lines. This option here is when you really want to drill down into all of the information about your job. This is one of the things we'll use to troubleshoot jobs, or an initial first step, and a great way for you to review a lot of information about your job, including a review of the resources you requested, a review of your utilization. So it'll tell you your CPU utilization, your memory utilization, your GPU utilization. There's a lot of really great information here to be able to look at what you requested, what you used, and learn from that to modify your script. The last 8 lines you can see here, the very top one, so it's about 8 up from the bottom, is the same comment we used to in the QStat-S search. There's a few other bits of information here, like the eligible time. This is the time your job is accrued, so the time it's eligible, the time it's been eligible to start running. So this may not have accrued any time yet if your job is not yet eligible to run. There are some reasons for this, which we'll talk a little bit about more tomorrow. But one thing to note there, the arguments would be your PBS job script, and then you won't always see this, but sometimes depending where your job is at in the queue, you may see an estimated start time. This isn't always 100%, so you can't always come back to us and say, my job was supposed to start at 5:12, 35 seconds after. It hasn't, what's going on? But this is an estimated time when your job should start. So at the very least, it's a good place to start. Why isn't my job running? Check the comment, and then after that, you can see if there's anything there, or you need to drill deeper. And one other thing, when you see those insufficient resources, we do remind people to be patient. We want your job to run as fast as possible, but it can sometimes take a while to run because Sockeye is popular. It's very great for researchers. People love it. I hope everyone loves it, but it is because of that, it is under high demand, especially the GPUs. The GPUs can be particularly popular, and large CPU and memory requests, large deep GPU requests can sit in the queue for a little while. So if they're not running instantaneously. If they're not running in a few hours, 8, 10 hours, be patient, submit it in the morning, submit it in the afternoon, come back the next day, take a look in the comments. If you're coming up on a few days, coming up on a week, and it's still not running, certainly reach out to us and we'd be happy to take a look into it for you. But there may be some clues in some of those why isn't my job running comments, for example, that can give you an idea of why it's sitting where it is. We'll talk a little bit more about some of this tomorrow in our general running jobs section. And this is again where it is advantageous to review your previous jobs to ensure you're not over requesting resources, which can impact the amount of time you're waiting. One thing I'll touch on here, which is why we're not also speaking to multiple GPUs, there is a bit of a learning curve with allocating multiple GPUs to your analysis. Different programs do it in a different way. So speaking, and we'll touch on it more shortly, but speaking to that model of the GPU and CPU communication, the CPU needs to allocate data to the GPU to run. This is done somewhat differently for different programs. So you can't necessarily, for all of your work, add more GPUs and expect things to run faster. You may still only be allocating this data to a single GPU. It's not being spread out across multiple. So it's a trip up with, I think, CPU only jobs, but also GPU jobs. More doesn't by default mean faster. You have to ensure that those resources are being utilized within your analysis script. So getting on to how is my job doing? You've submitted your job's running, everything's going great right now. One of the standard tools that we have pre-installed in Sockeye for you to use to get a kind of a live real-time look at how your job's doing is NVIDIA SMI. So NVIDIA SMI is the NVIDIA System Management Interface. Not at all helpful, but for those of you that like to know what acronyms mean, that's what it is. What it does tell you, though, is the GPU status. So some GPU health, memory usage, GPU utilization, and other information such as power consumption. This is great at giving you a live snapshot of whether your GPU is actually being utilized and by how much. It's accessed on the compute node your GPU is running on. So this is where I'm going to try a bit of a live demo. If it doesn't work, I can show you the pre-cooked version. And this is also the steps you would do to get in there. So how is my job doing? I would submit my job from the top, Q sub GPU job with your script name. I would query which node your job is running on. So again, I'm taking advantage of the QStat command. I'm modifying this with the N1U option. So we're going to talk more about the U option shortly. That allows us to query a user or your individual queue. And instead of typing my CWL, I've used the user variable. So this is just a key value pair. User is a key that stores your CWL's value. To call that, I put the $ in front of user. So $ user equals my CWL. Similarly, I can do qstat -n1u my CWL JCYC LE3, which you'll see shortly. But you can certainly use this as well. And then the N will output the node that your job is running on. Once you've found that node, you SSH into it. So SSH SC066, and then you can run the NVIDIA SMI command. So let's see how we do here. Okay, so I'm just going to log into Sockeye. Can everyone see my terminal okay? I'll make it a little bit bigger for those in the room. Only goes so big. It's going to be obscenely large for me, but hopefully. Okay. So I'm going to change into my Scratch directory, and I'm going to apologize to Nick for my poor data management practices. And I'm going to submit a job, PyTorch. I'm not going to show you what this is actually doing. One, because Jacob is in the room. Oops. And I think I saw Wade on the call, and it is just very abusive of the GPU. Basically, it's a speed test between CPU and GPU, and then I'm just looping the GPU test an obscene amount of times just to keep the GPU busy. So not ideal, but it works for this, so I can demonstrate things. Okay, so I've submitted the job, qsub, my PyTorch GPU. It outputs the name of the job here. So what I can do is I can go, if I want to see if my job is running, we'll talk more about this tomorrow, but that U option. Is it running? It's not. There we go. Okay. So we can see for the status, we'll talk about this more tomorrow, but my job is running. If I actually want to see which job which node my job is running on, I can use the N1U. And on the bottom right here, I can see I'm running in node SE063. I'm going to SSH into that node, similar to how I do with Sockeye, except I'm not going to input my user address. I've logged into this node before, so I'm just put in. You may see something similar, something where if you're logging in for the first time, you get a message, do you trust this? You can enter yes. And then I'm going to run NVIDIA SMI. And the output is taking a moment. There it is. Okay. And then from here, we get the NVIDIA SMI output. We may not see my work just yet because I have PyTorch set up with a virtual environment. It can take a little while to spin up the environment, import Torch, load the data into the GPU, as I mentioned, and then actually work on the GPU. So sometimes you may have to refresh this. There are ways you can have this run on a loop. We don't recommend using sort of the standard way because it can be somewhat compute intensive and a bit of a waste of resources, but we can also suggest some ways to monitor this live or more live. But at the very least, this is a nice way to see if and when your code is running on a GPU. So as I mentioned, here I am. I'm running at 100% utilization, so I'm crushing it right now. Again, because I'm kind of just abusing things, so it's actually not really an effective use, but I've got great utilization. We can also see in the middle column here how much memory I've allocated to that GPU. So 5,000 of 16 or 5 GB of 16. So that's kind of a nice snapshot of the memory that's currently there. And I can see how my job is doing. One thing I've seen before in some of my work and something you may sometimes see yourself is not super utilization. And that might be a time to then go back to your script and see where some of those bottlenecks are, which we'll touch on shortly. Another command, which we'll touch on very briefly, but more tomorrow in the running jobs, is you can also use the top command to review your CPU and memory utilization. You might bounce around depending on what's going on the CPU side of things, but you can see I'm near the top running the Python command. And so that's a live look at your non-GPU consumption. And I'll press escape to exit that. Oh, Q, I mean. And I'm going to exit the GPU node for now. And I'm back in the login node. Now I think when I ran, so when your job finishes, what you can do is run that qstat command that I mentioned to review your full job information. I'm just going to pull up the finished results from a recent GPU job. This one's probably going to run for about 15. Actually, what I'll do. So what you can do if your job is lagging, your job isn't running, it's in the queue, it's sitting there forever, you want to change something, you can delete your job with the qdel command, and then this will cancel your currently running job. I am going to look at an output of the qstatf command. And so this is if you were to run qstat in this case, or for completed jobs, you're going to need to modify that -f with the X or -xf option. And that allows you to look at finished, failed, somehow completed jobs. So this is actually not the job that I wanted, because it does not show good GPU utilization. Actually, it doesn't show the GPU utilization. Yeah, I could call Jacob. There we go. Okay. So this is what the output, and this is the live output of reviewing a job with qstat-xf job ID. So some of the things you may not care about, but if you want to check the job name, who owns it, CPU utilization. So mine was pretty terrible here. But where you're, and we'll talk a bit about more of all, a bit more about all of these tomorrow. I guess we're about an hour and a half into the instruction. What you're really going to care about here is your GPU utilization. So the duration that your job was running on the GPU node. You may be interested in the power consumption, but where you're also going to really be interested in is the maximum of GPU memory used, bit on the memory clock average, the memory utilization per node in percentage. So here, my average was 35%. I had a maximum of 76%. And then if we get down to the GPU utilization, as I mentioned, I was crushing it. You may not see this for your own, but you can see the average, maximum, and minimum utilization for your GPU job. So if this is something where you're only seeing maybe 1 to 3%, 1 to 4%, you're probably not utilizing the GPU as much as needed or at all. And this is somewhere where you really need to then modify your job script to ensure better usage of that GPU. Even something low, like 10 to 15, 20%, can certainly be improved quite a bit. We'd be happy to work with you on that and try to get that up. But this provides a nice kind of live look at how things are going. I'm just going to go back to my presentation. Everyone can see that? Perfect. Everyone's good on Zoom? Okay. So there's your NVIDIA SMI demo. Great for a quick snapshot of how you're doing. Is the GPU being utilized? How well is it being utilized? There are other profiling options. It does get more complex, and it's something we can discuss with you offline. We're certainly happy to provide future sessions on it, work with NVIDIA to provide some higher level training on it. But this is for a lot of people that have sort of a lower level utilization. This is at least good to raise some flags that I'm not utilizing GPU well enough. Where should I go in and start looking at things? We touched on how did my job do, the qstat-xf job ID. Had a demo there, so let's check. And this section's finished. We have one more to go. Do I have any questions on this section before we move on? All right, last section. Everyone is, you're all troopers for hanging on through all of these. So GPU utilization, considerations for effective utilization. This is going to be a little bit general, a little bit high level, because we are going language agnostic here, but there is a lot that can be sort of ported or applied at a high level to whichever sort of program you're working on. Getting back to that big picture at the start, it's always important to remember that your program starts on the CPU, sorry. You're copying data to the GPU and running the CPU is providing instructions to the GPU for what to do. Computations are performed on the GPU and the results copied from back to CPU. So it's good when you're doing this to then conceptualize, is data getting onto the GPU, and is data getting, is the right data or is the right analysis being done on the GPU, and how well. So then back to this picture, very basic diagram, but I think there's a lot of good information in here. One thing to remember, as the CPU and the GPU communicate, one of the biggest bottlenecks is that communication between the CPU and the GPU. That PCI bus is one type of interconnect. There are different types of interconnects for CPUs and GPUs. I know between GPUs, we're using NVLink. I'm not sure what we're using between GPUs and CPUs on Sockeye, to be honest, but there is a fair amount of latency there between transferring from the CPU and the GPU. Going back to that kernel definition we touched on at the beginning, there is also a bit of a lag in spinning up that GPU kernel. So if you are interested, or if you are wanting to kind of learn how to use GPUs by running some speed tests, comparing something on a CPU versus GPU, it can actually be advantageous to run that GPU job or that GPU set of instructions a few times to see how fast it is once that kernel's going. And this is where GPU effectiveness really comes in, is for those bigger jobs. If you're running smaller jobs, smaller batch sizes that aren't keeping the GPU busy, then you're often just better off running that job on the CPU itself. So a few sort of high-level considerations. Well, a lot of these are kind of interrelated. I'll discuss some details of all of them. There's definitely more than this, but I kind of wanted to take a bit of a shotgun approach to everything. And I'll certainly tap Jacob if there's, or Wade online, if there's something else they'd like to add, or more that they would like to add, because they're certainly have more expertise on this than myself. But one of the sort of basic ones to start with are, as I've mentioned, are you allocating data to your GPU, especially with a multiple GPU request? Is it only being allocated to one, or are you sending data to the GPU at all? A common programming method with PyTorch, for example, is to set the device to CUDA if CUDA is available. And that way, if GPUs aren't available, it's going to run on GPU, or sorry, on your CPU. And if GPUs are available, it's going to run on your GPU. That said, you may want it to run on GPU. So you do need to make sure that your code is written such that you're allocating data or information to the GPU memory. I have already touched on a few times the overhead of moving data back and forth between the CPU and GPU. So there's a few moving parts there. One of them is having enough to run on the GPU to, one, overcome the initial lag of starting a GPU kernel, as well as to overcome the lag of moving data from the CPU to GPU and eventually back. The other thing is you need to consider what computations, I would say, you're conducting on the CPU versus the GPU. So as an example, if you're creating tensors with something like PyTorch, it may actually be more advantageous to create that tensor on the GPU rather than creating it with your CPU and then moving it over to your GPU, because there is going to be some latency in that transfer. this again bleeds into what I've just discussed a little bit, where are the calculations being performed, what is being performed on the CPU and GPU, and what is best suited to be performed on each, and how much data, what do you need to move back and forth to perform. Like, are there computational dependencies between the CPU and the GPU as your script runs? Another consideration is, are there enough CPU workers to pass data to the GPU for processing? So this could be a compute bound issue. There's different ways of assigning workers with different programming languages. So getting into workers and data loading, data can be passed to the GPU in parallel. Some languages will use different methods, but it is worth exploring how that work is being conducted. It is okay at times for the CPU to be idle. You're never going to be able to get, or in most cases, you're not going to be able to get to a point where CPU and GPU are all fully utilized all the time. The main thing is, if you're running with the GPU, you want to make sure you're giving enough work to the GPU for it to be fully exploited or to be advantage to your research. The data loading is ensuring you're pushing enough data to your GPU memory and as quickly and as effectively as possible. Different programming languages will have different methods for this, including parallel methods of doing it. And the one other thing I'll mention here is pinned memory. And that's just allowing easy access to memory for your GPU and CPU communication. So you can pin memory on the CPU or on the host side of things for quicker transfer to the GPU. There are some caveats with this. So we wouldn't suggest you just pin a ton of memory, because that can actually then impact your utilization or the CPU side of things. But there is kind of a happy medium for increasing your performance. And with that, I think we're about 5 minutes early there. Because this was a pretty high level, I might stop there. Jacob, I don't know if you'd like to add anything, or Wade, you'd like to add anything, but otherwise happy to take any questions, and thank you for today's session. Great. And of course, always feel free to contact us at arc.support@ubc.ca. What is covered at 1 p.m. today? Today is software installation with Jerry. And so we'll be talking about some of the things I mentioned today, using modules in deeper or in-depth, installing tools with virtual env and conda, and singularity containers. We'll also briefly touch on installing your own software by other means, but that is more of a complex thing. So we would encourage you, if one of the other 3 methods isn't available to you.
Wait,
Otherwise,
is there anything you want to say? Okay.
No, the only thing I was going to say is, Jeff did mention things like your CPU efficiency or GPU efficiency and using as much as possible. Just know that you may be fighting a little bit of a losing battle as well. So it's, if your numbers aren't, what Jeff's benchmark was showing, don't beat yourself up about it. For a lot of users, they're kind of they're really at the mercy of the application developers to do a good job of it. And it's not a bad situation to be in, but the pace of available GPU resources has sort of outstripped the pace of developing software that can use all those resources efficiently. So, it may or may not be your fault if you're not getting the numbers that you think you should, but it's definitely good to try to optimize those.
that is a great point, Wade. And I should give the caveat that I am far, far from a extremely competent GPU programmer. As I tried to mention, my PyTorch code is pretty abusive and not true to life. It's not going to give you anything effective other than a massive stream of numbers that don't really mean anything. So my utilization, don't look to achieve that. I think if you're getting, even 40 to 60%, that's fantastic. And you're going to see some great performance with GPUs. I think the people we'd really like to hit, the people we'd like to work with, and the people that we'd hope can take something from this to improve is those that are anywhere from 0 to 10%, I'd say. Those are the ones that really aren't using GPUs at all or using it effectively and can really benefit from some of these considerations and then further work from with us to improve. Definitely don't aim for 95 to 100. It's not super realistic in real life.
Yeah, they're really incredibly powerful resources, and keeping them busy is their job in and to itself.
Yes, question.
I have a question about the live demo. So in the live demo, you show that you can SSH into the compute node that you're currently working on, and you can run NVIDIA SMI and get the output. You can run top and get the output. So my question is, if you can SSH into the node and run programs and receive the output of those programs, doesn't that effectively make it interactive?
So yes, it technically it can. I want to say this somewhat delicately because I think there's ways some workarounds there, but if you can SSH into a node, and that's how, sorry, I'm going to back up for half a second and repeat the question for those on Zoom. Technically, yes, if your job is running on a node, then you can the question was, if you can SSH into a node, run NVIDIA SMI, run top while your job is running, could you technically run interactive commands there? The answer would be yes, but you could potentially see performance issues with that. And you could impact the performance of other users. So as part of, I think, being a good HPC citizen, we would try to discourage that. That is something we also monitor, and we'll reach out to people if it's not a job script that's running on that node. Even something like an NVIDIA SMI -L option, where you're just looping through that command, can start to be more resource intensive and impacting the performance of your job and other jobs. So for that interactiveness, we would recommend just using the interactive node and then stick to the SSHing into the node for some of the live performance analysis. I don't know if that helps at all. Yeah, okay, yeah. And I think the one other thing I will highlight for all is you only be able to SSH into that node while your job is running. If your job isn't running or you're in there while when your job finishes, you'll be booted out. So you can only be in there as long as it's going.
Okay.
Yep. Yep. And we will pick up on it. For example, if you submit a dummy script and then try to SSH into that node and run your analysis interactively. I'm not saying you, I'm just saying the general you. It is something that we do actively discourage, but it is a great tool for live monitoring.
Okay.
Yep. Great. With that, I think I'll stop, and we're at 10:02, and yeah, we look forward to seeing everyone at the software session this afternoon, running jobs and parallel computing tomorrow. Thank you.